Hello, I am Jonas, and this is my Biomechanics Sport Report. In it, I will discuss the function of the flexor carpi ulnaris in the playing of tennis. The flexor carpi ulnaris is a muscle on the side of the forearm. It is long, thin, and multi-headed. Multi-headed just means it attaches at multiple points. In the diagram on the right is the muscle highlighted in blue, and the multi-headed part can be seen in the fact that there's a top left corner and a top right corner. It is located in the opposite side of the forearm from the thumb, stretching across its length. It is medial and superficial, which is just jargon for saying that it's close to the midline of the body when the palm is facing in front of you, and close to the surface of the skin as well. It originates near the elbow at a humeral head and an ulnar head. The humeral head in the picture is the top right corner, and the ulnar head is at the top left corner. In the wrist, it attaches to several bones. It includes the pisiform bone, which is an irregularly ball-shaped bone near the pinky side of the wrist. Another is the hamate bone, specifically its hook. The hook of that bone, despite only being 1 to 2 millimeters in length, is the central part of the wrist joint. Finally, it inserts into the fifth metacarpal bone, which is in the base of the pinky. The FCU is the primary flexor of the wrist. In anatomy, rotation across different axes are described with the following terms. Abduction is movement away from the midline, and its opposite is adduction, movement towards the midline. This would be rotating your wrist or your hand left to right. In contrast, there is also extension, which is straightening a joint and increasing its angle, and flexion, which is bending a joint and then decreasing its angle, also opposites of each other. In this last one is the main role of the flexor carpi ulnaris, although it also has supporting roles in other movements, such as in the adduction of the wrist and also the flexion of the elbow and forearm, as it is mostly in the forearm. The mathematical model for the flexor carpi ulnaris is very complicated. It receives motor signals from the ulnar nerve, which passes between its head and down the forearm. The wrist joint it attaches to is condyloid. So looking at the picture on the right, you can see how that lower shape could rotate in multiple different directions. The upper shape could rotate in multiple different directions if they were slotted in each other. They are connected with strong ligaments on each respective side, so a smooth surface is formed. Because in actuality, there's many bones, separate bones and muscles interacting with the joint. Motion in the proximal carpal radius begins only when the extrinsic ligaments crossing the mid-carpal joint become taut, and the force applied to the PCL becomes greater than the frictional force of the intervening articular segments and the resistance of the antagonistic muscular forces. This is from Anatomy, Biomechanics, and Loads of the wrist joint. The PCL is the concave arm side of the joint. The distal carpal radius is the convex hand side of the joint. These are very easily understood separations of the joint, and mostly accurate to how they move, but the biomechanics of the joint is still not fully understood, or at least modeled. There exist 6 more theories in that article that divide parts of the wrist joint differently. It also says that the wrist is a complicated anatomic structure and is considered the most complex joint of the human body. The flexor carpi ulnaris specifically is involved in the radiolunate joint, subjoint part of it, which transfers 35% of the force on average. This gives us some sort of tool for creating a mathematical model. For this one, I decided to determine or relate the work done by the muscle and also the angular velocity created in the hand. So I started with a kinemax equation. Omega is equal to alpha times time, and solve for alpha to get omega over time. Then I used the angular form of Newton's second law. Torque is equal to moment of inertia times alpha. And then here's the extraneous part. Only 35% of the force is effectively transmitted by the FCU, as it's primarily involved in the radiolunate joint. So we can add a coefficient of 0.35 to the torque in this equation. So we did that, and then to achieve the walk equals a moment of inertia times omega squared formula, I decided to integrate both sides with respect to theta. So I got walk on the left side, and the inverse of 0.35 reciprocal times integral of I d squared theta over d, or integral of I d theta over a d squared time with respect to theta. Finally, completing this integral on the right side, I just multiply the thetas out to get omega squared, and I could get rid of the integral sign. And that's then the final work done in creating angular velocity from the flexocopian inertia into the hand is determined to be 10/7 times the moment of inertia of the hand times omega squared. Now is the sport report part, as it is the biomechanics sport report. So in tennis, the reasoning that the flexocopian inertia specifically would be involved is under the assumption that you provide torque to the racket via the wrist, and that this torque is primarily or only in the FE axis of using flexion for this report. And side note, it is absolutely not this way. Not only do you probably provide multiple axes of rotation in playing tennis, but the torque is probably also non-constant, as it is based on many factors. But alas, the flexion of the flexocopian inertia is going to give the racket some angular momentum, and then when you hit the ball, it is assumed to be transferred completely elastically. And then the final angular velocity of the racket is assumed to be 0. So in other words, all the angular momentum of the racket is transferred to the ball. And the ball has initial velocity too, or initial momentum as well. So in the conservation of momentum equation, we see two terms on the left side and a term on the right side. Momentum of the ball and the racket equals the final momentum of the ball. And also, side note that whenever it says mass of racket or velocity of racket or hour of racket, that's really meaning the hand and racket system, as they do move as one in this model. So the first step is to change out the velocity of the racket for the distance to the pivot of the racket times the omega of the racket. And then we can use the prior equation, which relates walks to omega, to solve for walk here. So yes, we solved for omega in the walk equation, the energy equation, and then we substitute that in after also solving for omega in the momentum equation. And then I squared both sides. I multiplied by 10/7, and then I just multiplied by moment of inertia of the hand and racket system. And then I put it into Desmos, so it looks good. And we get the work done by the flexocopian inertia and giving the ball its final velocity after a collision, an elastic collision in tennis, is given to be 10/7 times the moment of inertia of the hand and racket times the mass of the ball times the difference in the final velocities of the ball, or the velocity and the starting velocity of the ball before the collision, over the mass of the racket, hand and racket system, and times the distance to the pivot point of the mass and racket system squared. Everything is squared except for the 10/7 time moment of inertia, that is. So there are many variables in that equation. However, many of them are in fact just constants for our purposes. The mass of the ball and the racket can be measured, always unchanging. The length of the racket, if we assume a set collision point, is also unchanging. And then the moment of inertia of the hand and racket system is a constant. However, it is given across some calculations. The three final unknowns include two dependent variables and an independent variable. And for our purposes, we're treating the velocity of the ball before the collision as always unchanging, although this can just be calculated. The work is the independent variable, and the final velocity of the ball is the dependent variable. So, in determining what the initial velocity of the ball, I decided to go with the first swerve of the game. So, I set up an example scenario where a player throws the ball 0.5 meters up, and then hits it when it returns to chest level from whence they threw it. So using the v squared equals 2 delta x formula in kinematics, we get the initial velocity of the ball to be the square root of gravity, or 3.13 meters per second. The moment of inertia of the hand and racket systems is not so easy, however. We need to use a very rough approximation, using the formula moment of inertia equals the sum of m times r squared, and treat the system as three separate point masses. One point mass is in the hoop of the racket, the other point mass is in the handle and supporting beams, seen in the picture of the handle, and that final center of mass is seen in the hand. And then we could simply take the mass of each respective center of mass and multiply it by the distance to the pivot point squared, which is the wrist, to determine the moment of inertia of the system. These 14 measurements were used in the determination of the moment of inertia, 2 of them from the internet. The mass of the hand and racket, which also conveniently turned out to be this exact same. From then, I calculated the volume of the hoop and the handle, and also the handle and supporting beams of the racket. The hoop was treated as an ellipse with a depth and a width. And then to find the mass of the center of masses in the racket, I used the portion of volume, over total volume times the mass of the racket. And then finally, using the measured mass of the components of the racket as well as the mass of the hand, and then also using the measured radii to the pivot point, I calculated each individual moment of inertia and then added them together to get a final moment of inertia of around 0.04 kilogram times meter squared. These variables all the variables were substituted. And then the new equation, after cleaning up a lot of the constants, we got work is equal to 0.0017 times the difference, or the final velocity of the ball minus 3.13 squared. A quadratic, in other words. This actually still fits the W equals, or work equals I omega squared formula for energy, just with a heavy coefficient, or heavy difference in coefficient, as well as a horizontal shift. So to compare this equation to determine its reliability, I determined the average energy of a bullet, about 313 joules, and I found that this gave the energy of the tennis ball moving at that same speed, although it has 6 times as much mass, to actually take a third the amount of joules, amount of the energy. So yeah, it might have some inaccuracies. However, I do want to point out the horizontal shift. This is actually an accuracy of the equation, in my opinion, because if the velocity of the ball remains at 3.13 meters per second, that means in the collision, it's just gonna keep on bouncing forever. So no work was put in to change its velocity. I do believe that the fact that it takes positive work to decrease the velocity of the ball is an extraneous result, though, the y-intercept being positive. Finally, I propose some sources of error for this situation. So many of these I've already explained. Yeah, I think the most important one is probably the fact that you mostly do not use the flexor carpioneus or the radiolunate joint in the manipulation of the racket with your hand. It probably usually moves in multiple different axes at multiple different rates. So the 35% efficiency might as well be like a third of that, or even lower efficiency of force transmission. And finally, here are my sources. Thank you.